So Na2CO3, I'm going to find it. Negative 11331. 1131. Make sure you're paying attention to whether it's the delta H or the delta S. All right. Let's see, times 1, so that's fine. Plus my CO2 is negative 393.5, and my water is negative 242, and my big subtraction sign, so do that, and it's 2 times this one, negative 948. And the units on all these are all in kilojoules. So we type this in. Uh-oh. Might type that in. Don't forget to put negative 2 times negative 948. Negative 11131 plus negative 393.5.
Shouldn't it be plus negative 242?
Sure is. I need some algebra in my head.
1,766. Oh no, hold on.
Whoa. All right, ball, there's 400, negative 15, negative 17. Well, it's gonna be tight. I'm gonna say positive 300 or something. I don't know. Did I type it in?
I got negative 818.
Negative 800,
818.5.
18. What you got? Mike?
0.5.
Is that what you got?
No.
Nope. What'd you get?
0.5.
149.5? 29? But positive here. Uh-oh. You guys need calculators. Making me pull mine out. Terrible. Okay. I guess when you're serious, it's bad enough you should quit quoting me. Right?
He's right. He's right. I did multiply that last number by 2.
Ah, okay. You fell for the old hidden one there. So positive 129. What does that tell me about this reaction?
It's endothermic.
Endothermic. Good. All right. Now, wait a minute. This is in kilojoules. What would it be in joules?
Times 1,000.
Okay.
Or it's in kilojoules with 1 joules. It's divided by 1,000.
No, you're right the first time. Times 1,000. All right. So
no, don't we have to divide by 1,000?
Do what? You multiply by
Do we
1,000.
have to divide it by 1,000?
No, that's going from joules to kilojoules. You divide by 1,000. Now, why do we need both? We'll write down the kilojoules so we can always. Then they wanted the delta S. So I'm going to just change some of these numbers. I'll change that number, this number, this number, this number. changing it to S's. And I'm looking at the next column. So my products, my Na2CO3 was plus 136. So 136 plus my CO2 plus 214. My water is 189 minus 2 times, and this is 102. Oh, now we type this in.
335.
335 kilojoules. No, I take that back. This is joules per Kelvin. Which will be 0.335 kilojoules per Kelvin. So I've got one out here. I'm just gonna write the kilojoules. And then it's per Kelvin. We gotta multiply by the moles. No, it should just be joules, kilojoules. All right, and then he probably asked us to find delta G, figure out delta G, kilojoules and joules, make our life interesting. So we need to go back and look up that Celio R number. Anybody remember what it was?
8.312 or something.
No, so close. 0.3142. Do you remember what the units were on that? Joules over mole. Mole times Kelvin. All right, good. Was it, the key was it joules or was it kilojoules? It was joules, all right? So why is that important? Is when I go plug in this stuff into this equation, that's going to affect my kilojoules versus, so if I plug these in, and I got this, wait a minute, this is my delta G. As long as I have the same, I'll be fine. I didn't need R until I go to find that L, N, and K business. So this one's not too bad. Let's do, which one do we want? Let's do joules. This was 129,500 minus temperature was 298. And now that's at 25 degrees Celsius, which is 298 Kelvin. This, you'll see a lot in our examples. And if you've never been told that, that's what we used to call room temperature. Room temperature. And that's a problem now, because since the advent of air conditioning, nobody keeps their room at room temperature anymore. We use it for convenience. So when you're working these problems, you'll see 25 degrees Celsius is the given conditions a lot. It's become a standard, but it's not standard temperature, which is 0 degrees Celsius.
I mean, just for the sake of like a question on a quiz.
It's, so this is one you'll see a lot, and that's why you see a lot. It used to be called room temperature. So we still say room temperature at that. That's about 77 degrees Fahrenheit. So everybody keeps their air conditioner going. It's actually lower than that. So that's why you'll see it use these examples a lot. All right, so then our delta S here in joules was 335. Oh man, somebody will have to type that in. Okay. Uh-oh, how do I want K. How do I get rid of that LN?
Divide.
Divide both sides by LN?
Yeah.
Well, see, I can divide both sides by negative RT. You go delta G divided by negative RT. That'd be equal to this LN of K. But I can't divide by LN. That's its own math function. How would I get rid of log? Does anybody remember? 10 to the log. And I raise both sides. Here I'm going to do the same thing. I'm going to raise both sides to the E. So these two LNs cancel out. E and the LN. So we're looking for E of our delta G divided by negative RT. Almost, right? So this is on the reactant side. This reaction done 8.45 times 10 to the minus 12. That's what I got. Unless somebody got somebody different.
And it favors reactants.
It would favor reactants. Now, a lot of this is, so that was the first 4 questions. We spent all that work. But then we got 8 more questions. Man. And so there must be more to this than just the numbers. Matthew, you getting a different answer than me, or you just? Gary. All right, Matthew, on Tuesday, Thursday. Thank you, Gary. Sorry about that. What'd you get?
My calculator says 0.
Said 0. Came out to be really close to 0. 0. Okay. You said flat out 0? Yeah. All right. We'll back. All right, so what does this mean with delta H? What did we decide?
It was.
Is it positive? Yeah, it's positive, right? That 129.5 kilojoules?
Yeah, positive.
Positive. Is that endothermic or exothermic? Endothermic. Which picture describes endothermic? The left or the right? The right is endothermic, right? It's higher on the products. Good. All right. Which side will heat be written? If it's endothermic, is the word heat going to go on a reactant or product side?
It'll be on the reactant side.
It'll be on the reactant side. So that list I gave you at the beginning for endothermic versus exothermic, we have to look at it. All right, this delta S is telling me I've got more entropy, more disorder in my, so it was a positive delta S.
Mm-hmm.
All right. So that means I had more in my reactants. Nope, I had more in my products than I had in my reactants. More in my products than I had in my reactants. More disorder. Does that make sense? We took a solid and broke it up into a series of gases. Would I have more disorder when I have a bunch of stuff moving around? Sure. And it says, would I know that sign? But when I come back and I look at the equation, I had one solid, I had 2 molecules of it, or 2 moles of it, and we broke it up into 3 different things. And here I got 2 different moles of these that are gases. So there's much more disorder on the right-hand side. So there's more disorder in my products than in my reactants. Did I get that? The K, we said it's mostly reactant favored. And what happens to the number of moles of CO2 and H2O if we lower the temperature? Uh-oh. If I lower the temperature. Here's how you answer that. It's a Le Chatelier's question. Oh man, we're running very late. Oh no. The Chatelain's question, heat's on the reactant side. If I lower that, it's going to shift to the left. It'll lower the CO2 and lower the water.